To motivate the topic of this video, let's talk about circles. So in particular, I want to think about a circle of centered at the point AB with radius r. What's the equation of the circle, or what's an equation of the circle, I guess is a better way to say it. X minus a squared plus y minus b squared is equal to r squared. So this is how we usually write equation for a circle. If we take the square root of both sides here, we would end up with r is equal to the square root of x minus a squared plus y minus b squared. And so what is this expression here? This right-hand side, by the discussion we had in our previous video, this is just the distance from the point x comma y to a comma b, and saying that the distance from xy to ab needs to equal r is saying that this distance must be r, a constant. You know, one very elegant way, and probably the most elegant way to define a circle, is just to say it's the set of all points at distance r from your center point. So if this is a comma b, and I say, okay, this right here is r, a circle is the set of all points at distance r away from a, b. Well, now we're thinking about, so this is all prologue here. Well, now let's talk about three-dimensional space here. We had this distance formula here in R3. Well, now let's think about equations for spheres in R3, spheres in space. So here we have radius a, center at x naught, y naught, z naught. The equation here is x minus x naught squared plus y minus y naught squared plus z minus z naught squared is equal to a squared. So this right here is the equivalent in three-dimensional space of our circle equation, generic circle here. Once again, let's just kind of compare x minus the x coordinate of the center squared plus y minus the y coordinate of the center squared. Up here, there's an extra plus z minus the z coordinate of the center squared is equal to the radius squared. Here I use r, there I use a. That shouldn't bother us. And again, why does this work? You know, let's just note here that real quick that we take the square root of both sides. Square root of x minus x naught squared plus y minus y naught squared plus z minus z naught squared is equal to a. So this is the set of all points at distance a from our center x naught, y naught, z naught. And we get this by, we just recognize here as this is coming from the distance formula in R3. Okay, so something that I could do here is ask you if I just say, write down an equation of a sphere centered at 1, 2, 3 with radius 4. You would just plop in, 1 in for x naught, 2 in for y naught, 3 in for z naught, 4 in for a. Maybe a slightly more interesting sphere question is this one right here that I borrowed from the book. Find the center and radius of x squared plus y squared plus z squared plus 3x minus 4z plus 1 is equal to 0. How do we tackle this kind of problem? We want to write it in this form. We want to write it as x minus x naught squared plus y minus y naught squared plus z minus z naught squared is equal to some radius squared. How do we do this? it's going to be a lot of completing the square, this old algebra trick. So let's rearrange this. So we put our x terms together plus our y terms together. That's the only y term. Plus our z terms. Z squared minus 4z plus 1 is equal to 0. So what I'm going to do here is we just have to fill in terms to be able to write. We can fill in terms, which we'd have to add or subtract to the other side. Things so that we're going to write them as x minus something squared, y minus something squared, z minus something squared. So one of them is really easy. The y squared here is just y minus 0 squared. So that's done. Z squared minus 4z, if we tack in a plus 4 here, we get z minus 2 quantity squared. So convince yourself that z squared minus 4z plus 4 is equal to z minus 2 quantity squared. How did I come up with 4? I divided negative 4 by 2 and got negative 2 and squared that to get 4. Okay, so we added 4 on the left, so we need to add 4 on the right. And then over here, we have x squared plus 3x, and then I need to add 9 halves to make this be x plus, not 9 halves, 9 fourths. Again, what do I do to complete the square? Take 3, divide it by 2, and then square 3 halves squared to get 9 fourths. So I'm going to have to also add 9 fourths to the other side. So where are we right now? X plus 3 halves squared plus y minus 0 squared plus z minus 2 squared plus 1, and that hasn't moved, is equal to 4 plus 9 over 4. Okay, let's move that plus 1 to the other side and rewrite this. X plus 3 halves squared plus y minus 0 squared plus z minus 2 squared is equal to 4 plus 9 fourths minus 1. And this crunches out as 21 over 4. So to finish off the problem, the answer on the right is the square of our radius. So this is really square root 21 over 2 quantity squared is equal to x plus 3 halves squared plus y minus 0 squared plus z minus 2 quantity squared. Okay, so we've done all of the work to put it into this form here. Now we just have to write down the answer. We just read off x naught, y naught, and z naught. So note, I should emphasize, this should be x minus x naught. And so really this term is, we're thinking of x minus 3 halves quantity squared. And so the x coordinate here for x naught will be negative 3 halves, and then the y naught will be 0, z naught will be 2. So this is our center, and our radius is square root 21 over 2. Okay, so hopefully that was an insightful example. To finish off this video, and in fact to finish off the section, I'm borrowing this one with a little bit modification from the book. Let's just write down interpretations of, what points satisfy all these equations. So x squared plus y squared plus z squared is equal to 4. This is a sphere of radius square root of 4 is 2, centered at the origin. And to be clear here, when we say sphere, it's only the surface. And the radius here is 2. So because this has to equal 4, the distance of these points away from the origin has to be exactly 2 here. So it's the surface of the sphere, it's not the filled in region. But if we do x squared plus y squared plus z squared is less than or equal to 4, this is the filled in sphere. This is a solid ball or a filled in sphere. Of radius 2 centered at the origin. So now, when I draw the picture, I'm going to do this, but let me emphasize, it's everything. It's a solid ball. And if you kind of burst, you could kind of prick this. There'd be air inside of it to get out. You scratch the surface of it, it's solid all the way till you get to the origin. And then this next one here, this one is just going to be the interior of the sphere. Not the boundary, not the surface itself. Because x squared plus y squared plus z squared is strictly less than 4, so all points that are distance strictly less than 2 away from the origin. It might feel like, we're kind of being tedious and pedantic about all this stuff. Later on in the class, these things, when we hit chapters 15 and 16, these differences will be important. And then one last one here, x squared plus y squared plus z squared is equal to 4. Z is positive. So we know this part is sphere, radius 2, center at the origin. This is the top, z is positive, top hemisphere. So I draw this picture, but then I only draw the top hemisphere here. There's no negative values of z. So it's half of the sphere. Again, this kind of stuff will come up later. We made z less than or equal to 0 instead of z greater than or equal to 0. It would be the bottom hemisphere. Okay, I guess that's a good place to wrap things up.